want theories in physics with the minimum number of variables or equations to describe as many as possible phenomena. For example, every physicist will tell you that Maxwell's theory of electromagnetism is fantastically beautiful because with just four mathematical equations, he could explain all the classical electromagnetic phenomena. Think about this. There is so much in electromagnetism, all explainable with four equations. That is considered absolutely beautiful.
I'm Brandon Vaidyanathan, and this is Beauty at Work, a podcast about how beauty works in our world and shapes the work that we do. Hello everyone, thank you for joining us today, and I am delighted to introduce my guest for this episode, Dr. Mario Livio, who is an astrophysicist and author. Dr. Livio is a fellow of the American Association for the Advancement of Science, and for 24 years, Dr. Livio worked with the Hubble Space Telescope. He has published more than 500 scientific articles on topics such as cosmology, supernova explosions, black holes, extrasolar planets, and the emergence of life in the universe. Dr. Livio is author of 7 books, including The Golden Ratio, Is God a Mathematician?, and Brilliant Blunders. His latest book is Galileo and the Science Deniers. Mario, thank you for joining us. It is such a delight to be able to speak with you. Thank you for taking the time.
Sure, thank you for having me.
Yeah, well, let's get started. Could you tell us what led you to astrophysics? What drew you to astrophysics to begin with?
Well, I studied mathematics and physics, actually, and emphasizing both. And I wasn't sure at the beginning, whether to go into mathematics or physics, but at some point, I decided on physics because I was kind of always interested in the universe, and physics actually seemed to be able to offer answers to questions about the universe. I didn't immediately go to astrophysics, however, also. I did a master's degree in particle physics, high energy physics, which studies the subatomic world, basically. Um, it just so happened that at that particular time there was a little bit of a decline in particle physics because in particle physics much of the work was driven by the availability of new accelerators, and it was a time kind of between discoveries in a way, while at the same time astrophysics was really picking up in a strong way. So after the master's in particle physics, I did a PhD in astrophysics, and never looked back. Now it so happened that the two fields, in many ways, have grown so close that I now have colleagues who came from the direction of astrophysics, direction of particle physics, and are doing similar things. And the same is true for me at some level too.
Okay. Are there moments when you were, in your childhood that you perhaps can trace as inspiring your desire to be a scientist, or drawing you to the
Well, I
space?
would say
Or
I was always extremely curious. I mean, I asked lots of questions, and I read a lot about science. I was not. I always had kind of theoretical inclinations, not so much experimental. I wasn't doing lots of experiments. People often ask me, did I have my own telescope to look, to the heavens? Well, we were quite poor, and I didn't have a telescope. Uh, I mean, I would have been happy to have one, but I didn't. Um, so I turned more towards the theoretical side of things.
yeah, great. And now, in addition to your career as an astrophysics, you've written a number of very successful popular science books. What drew you in that direction?
Oh, that that didn't happen very early in my career. I for many years I didn't write popular science books. But what I always did do was I was giving lots of popular talks to the public. I always kind of felt that at some level it was even our duty as scientists to make people not only understand what we're doing, but in particular appreciate the value of science. And so I was giving lots of talks. And then at some point, I believe around the year 2000 or so, I thought to myself, I'm giving so many talks. Maybe if I write a book, I will reach a larger audience than by merely giving talks. Um, so I wrote my first book. And well, since then, I wrote six more. So that's how it is.
That's lovely. Well, great. Well, let's talk about the role of beauty in your own work, and maybe a good place to start is defining beauty, which is something you take particular care to do in the Accelerating Universe. This is really enjoyed this book, and tell us you have a threefold definition, where you offer three criteria of what beauty means, at least in physics, right? So you talk about symmetry and simplicity and the Copernican principle. So tell us a bit more about this definition.
Yeah. So look, to define beauty is an almost impossible task. Uh, there probably are as many definitions as the number of people you're going to ask to define it. Um, what I tried to do in that book, and that in itself was hard enough, was to define, well, to try to narrow down a little bit. When does a physicist talk about a certain theory in physics specifically as being a beautiful theory? So it was not a definition of beauty, it was a definition of beautiful theories in physics. Um, and even that turned out to be very difficult because if you again look at many scientists even who talked about beauty in physics, they use many many words like harmony and balance and all kinds of words like that. And I tried to somehow focus on the things which I thought were absolutely essential in a way. Um, and I ended up with three concepts, as you mentioned. I mean, one was symmetry, and symmetry I put in because uh, most of the fundamental laws of physics they have a symmetry associated with them. In fact, all the laws that we call conservation laws, like people heard about conservation of energy, conservation of momentum, and so on. All of those conservation laws stem from certain symmetries. For example, conservation of momentum stems from the fact that the laws of physics are symmetrical under translation, which means they don't change from place to place. We see the same laws that we have here on Earth apply in a galaxy that is a billion light years away. The same laws of physics apply. Conservation of energy comes from the fact that the laws are symmetric with respect to time. The laws appear not to change with time, and so on. So symmetry is really, if you like, almost the source from which laws of physics stem. So that was clearly a necessary ingredient. The second concept that I introduced was simplicity, which I meant in the sense of reductionism, namely that you want theories in physics with the minimum number of variables or equations to describe as many as possible phenomena. For example, every physicist will tell you that Maxwell's theory of electromagnetism is fantastically beautiful because with just four mathematical equations, he could explain all the classical electromagnetic phenomena. This Think about this. There is so much in electromagnetism, all explainable with four equations. That is considered absolutely beautiful. Things like Einstein's theory of general relativity is thought by some to be the most beautiful theory of all. Um, it's first of all, it has lots of symmetries built inside it, but also, with this one theory, you explain everything that's related to gravitational force, and so on. Whether it is, uh, I don't know, tides in the ocean, or it is the planets moving around the sun, or how the universe as a whole behaves, and all that. So all of that is there. So that was the concept of simplicity. And finally, there is the concept that probably least number of people know what that is, which I call the generalized Copernican principle. And what do I mean by that? Starting from Copernicus taught us uh, that we, or the Earth, are nothing special. We're just another planet orbiting an ordinary star, and so on. Since then, we have gone through four more, if you like, Copernican revolutions. Um, Astronomer Harlow Shapley showed that in our own Milky Way galaxy, the solar system is not at the center, is some two-thirds of the way out. So again, nothing special. After that, Edwin Hubble and others have shown that there are many galaxies. By the latest estimate, maybe as 2 trillion galaxies in the observable universe alone. Um, the Kepler Observatory has shown that there are terrestrial planets a bit like the Earth in our own galaxy, in numbers like from a few hundred million to a billion or so. So in that respect, also we're nothing special. And finally, perhaps, there are some speculative theories now, which it's called the multiverse, which maybe even our entire universe is just one member of a huge ensemble of universes, and so on. So, in all of these steps, we have kind of progressed to a situation where the theory is not dependent on us being there, or the Earth being in a special location. So, and we would like both theories to do that. I should mention something though. The last step, which I mentioned, multiverse, that maybe there are many universes. Uh, that's maybe where Copernican humility meets its limit, because it is possible that in these many universes, the laws of physics are different, or the values of constant of nature are different, so that, for example, complexity and life could not emerge in them. So our universe is somewhat, if this ensemble exists, our universe may be special in this ensemble, not quite the same as everything else. Um, so, to give you a somewhat silly example, but which exemplifies this, is suppose you wake up in the morning and you wonder, what am I? Now, if you just went by statistics and by uh, not wanting to be special at all, you would say I'm an insect, because insects are the largest biomass on Earth. At any given moment, the estimate is that there are about 10 to the 19 insects. It's one followed by 19 zeros of insects. So, just speaking like that, chances are you are an insect, yes? But Why is it not true? Why is it false? And you are not an insect? Because merely by wondering about the question, what am I, you already distinguished yourself as being special and not an insect. Yes. So, yes, you want this generalized Copernican principle to be nothing special, but it does hit a limit at the end. So, we now hit that limit, for example, in this example.
Yeah, no, that's I mean that's really fascinating. You also dismiss, I suppose, the value of elegance, which is another sort of criterion that a lot of scientists bring up as not being particularly necessary for a definition of beauty in scientific theories, right?
No, I don't dismiss it. I mean, elegance is brought a lot in mathematics. I mean, people talk about elegant proofs. There are proofs that are shorter, usually, simpler, uh, somewhat surprising, and so on. Now, in physics, I think that this concept of elegance is captured by a combination of simplicity and symmetry. So this is why I didn't bother to list it separately, but elegance is certainly something very nice to have. And in mathematics, it's there definitely are problems where the proof is more elegant this way than it is that way. You find the answer in more elegant ways, and so on. So it's an important concept, but I wanted to be as reductionist as possible in my definition. So I did not list it as a separate
Right.
necessary condition.
Yeah, you see it as a function of other, yeah, of symmetry and simplicity. Um, Tell us about your own experience, in your own career. Are there moments of encounters with beauty that stand out to you in your memory?
Well, you not necessarily things that I have done. I mean, there are things uh, that clearly stand out to me as I just mentioned this element of surprise. Uh, the element of surprise is is very important, and well, it's captured in these other things. But yes, but it is important. By that I mean, for example, if I look at general relativity, which is this incredible theory of Einstein that describes gravity, for the life of me, I still did not understand how he thought about that. I mean, there are many things that are in the air. And, for example, special relativity, had Einstein not written it, somebody else would have within a year or two. Uh, Henri Poincaré was extremely close, to writing something like this. General relativity, yes, Hilbert was playing with some ideas like that and so on, but not so much, more in the mathematical sense, and somewhat less than Einstein's really concept of everything that there is. It wasn't in there. Similarly, I've written a book about symmetry, which was called The Equation That Couldn't Be Solved. And in it, I described this French mathematician, Évariste Galois, who died at the age of 20. But before the age of 20, he invented a branch of mathematics that today we call group theory. Um, that was not in the air at all when he formulated it. I mean, that, really blows my mind when I see things like that. Um, so those are the types of things that really, that when sometimes catches you by surprise like that. I mean, those are moments that I definitely remember.
Yeah. They seem to evoke a sense of awe, I suppose, right? I mean, the fact that someone can come up with something
That's
like
right.
this.
That's right. Yeah, but in this case, I mean, there is awe from the universe itself. Yes, which is so fantastically beautiful in itself. Yes, we all feel that. Yeah, you have to look at the new images of that came from the James Webb Space Telescope, or previous images that came from the Hubble telescope, and so on. And you just realize that not only are they almost as attractive to the eye as works of art, but at the same time, they actually represent real objects in our universe, which adds to it yet another dimension. So there is that awe, and then there is the awe that what the human mind is capable of. How could this young mathematician of age by the age of 20 do that? I'm trying to think. Yeah, I've had a fairly reasonable career as a scientist, but when I'm trying to think what have I done by age 20, the answer is absolutely nothing.
Yeah. Right.
This guy formulated group theory. I mean, it's
Wow.
amazing.
Yeah, yeah, it's astonishing. I mean, there's also, I suppose, that that famous Einstein quotation that the I can't remember the exact phrasing, but what is marvelous about the universe is the fact that we're able to understand it at all, right? I mean, the very fact that if you add that to your Copernican principle, given how insignificant we are in the scheme of things, it seems rather bizarre that we're capable of grasping the laws that govern everything, uh, and
Right.
or that.
Yeah, from a physical perspective, we're insignificant. But from the sense of what Einstein meant when he said that, we are extremely significant, because you see, with every step that I mentioned, for example, with these five Copernican revolutions, if you like, those revolutions meant that we as humans understood something new that we didn't know before. So our mind expanded precisely as fast as our physical significance diminished. So, in that sense, we really are central to
That's
everything.
extraordinary. Yeah. Um, I suppose. I mean, I wonder what you think about whether what scientists have found beautiful over the centuries has changed in that respect, right? So I suppose prior to Copernicus, maybe what might have been beautiful would have been things that established our centrality in the scheme of things, uh, as opposed to now things that establish how decentered we are. Do you see any changes, I suppose, over the centuries in these sort of fundamental aesthetic criteria that govern science?
No, I think it is more a matter of perspective. You see, for many, many centuries, uh, people thought that the the orbits of planets around the sun have to be circles, mainly because of aesthetic reasons. When Kepler discovered that the orbits are ellipses, Galileo, the great Galileo, did not accept that, because he was still also prisoner to this aesthetic idea that the orbits have to be circles. But you see, that came from a misunderstanding, because the symmetry is not of the shapes, the symmetry is of the laws. The law of gravity is symmetric under rotations, which means, yes, the orbit is an ellipse, but the ellipse can have any orientation in space, and all of those are allowed. Had Galileo been taught that, I'm sure that he would have found that these ellipses are also beautiful. It was just a misunderstanding, because at that time they still didn't have, the right perspective on
Yeah,
this.
yeah. Well, that's an interesting kind of question, right? So I suppose this leads to whether, I mean, there's this debate now in theoretical physics as to whether aesthetic criteria are reliable guides to the truth, right? So on one hand, you have, I think of people like maybe Hermann Weyl, who would say that elegant theories or equations are more likely to be true than those that are not. And on the other hand, you've got Sabine Hassenfelder, who's arguing that this sort of pursuit of beauty, beautiful mathematics, beautiful equations, simplicity, naturalness, these sorts of criteria are leading physics astray. What do you think of that?
Well, you see, physics is it has an additional, very very stringent constraint. Uh, the theories actually have to be correct vis-a-vis the universe that we see. I mean, that is the most stringent criterion. I mean, there is this phrase which says that my most beautiful theories have been destroyed by ugly facts. Uh, so, uh, the thing is that at the end of the day, uh, irrespective of how beautiful the theory is, it has to actually be able, number one, to explain all known phenomena at that given moment when the theory is proposed. And number two, the theory has to make predictions that can be tested by future experiments or observations. Otherwise, it is not a valid theory of physics. And this is irrespective whether the theory is beautiful or not. I mean, the Ptolemaic model of the solar system was a very good model in that it explained, the observations really quite well. It had the problem that it was a little bit too complicated. It had epicycles on top of other difference, and I don't know what. But in terms of explaining the observations, it was pretty good. And in fact, even the Copernican model, when it was first suggested, was not much simpler than they also had to add epicycles at the beginning to explain everything that was observed. Only later, when we discovered that orbits can be elliptical and so on, and things like that, then we realized that the Copernican model can be much simpler than the Ptolemaic model, which it wasn't initially, but can be made much simpler. And then it became, in my mind, a more beautiful theory, yes, a more beautiful model in the sense that it became simpler, even though it explained the same observations on. But first of all, they need to explain. So, for example, in the example you mentioned, string theory is has been considered as our best attempt to formulating a theory that combines Einstein's general relativity with our best theory of the subatomic world, namely quantum mechanics. It's an attempt to do that. And for now, good few decades now, has been considered perhaps as our best attempt so far. However, the theory so far has failed to produce testable predictions. So if it remains like that, irrespective how beautiful it is mathematically, it will not be an accepted theory in physics. And indeed, may have even at some level led us astray in some sense, in that very many of the brightest minds followed along that path, which maybe doesn't lead at the end. Now, it will it will never be without any value, because first of all, some truly remarkable mathematics has been formulated and invented in the context of string theory, and I have very little doubt that many of those concepts and branches of mathematics will turn out to be very fruitful in whatever theory at the end we can come up with, if we can come up with a theory like this. So it's not been a complete waste of time, but it may be that for a while we went in the wrong direction. I don't lament that. I mean, I wrote a book called Brilliant Blunders, and by brilliant blunders, I mean, you know, when people try to think outside the box or to think outside the mainstream, at least for a while, they may make mistakes. But sometimes these attempts they lead to breakthroughs. So string theory could have led to breakthroughs. It hasn't so far, and maybe it will never. So maybe it will turn out to be a brilliant blunder. You know, not, by the way, not a sloppy blunder, or I mean, it was not. It's not as if somebody was not thoughtful enough or this and did this. I mean, incredible work and genius work has been put into this. Um, and like I said, I mean, I believe that some parts of it will still be fruitful no matter what.
Yeah, yeah. I guess it's a question of whether it's testable or what testable predictions could look like. Or, I mean, similarly with multiverses, I suppose it's one of those things that people argue. Is this even physics? Or I think Jim Baggett calls it fairy tale physics. Or there's this idea that if this is not in principle testable, or we don't know how long we'd have to wait until we can even imagine what it would mean to test it, then what are we doing? And uh,
So here is my comment about that. You see, there are a good number of things today which are not observable. For example, it used to be say, when we say talk about the observable universe, our universe is only has a finite age, 13.8 billion years. So we can only see so far. But nobody ever suspected that there is nothing beyond that where from which we can get light. But the expectation was that as time goes by, we will see more and more of that. The observable universe will increase. However, we now know that our universe is accelerating. The expansion is accelerating, which means things that we have not seen so far, we will never see. Now, does that mean that those things now don't exist because we will never see them? No, nobody will say that. And yet we will never see them. So I think we should expand somewhat our notion of the scientific method to say, if you have a theory which makes lots of predictions in the observable universe, which can all be tested, yes, then you should accept predictions of this theory also in unobservable parts. You understand? But of course, it has to make lots of predictions, all of which are testable and turn out to be correct in the observable part of the universe. So that's the way I feel about the multiverse. The multiverse, yes, we may never be able to see anything directly from these other universes. But if the idea of that, makes lots of predictions in our observable universe, then we should, for example, I mean, the multiverse is, I wouldn't say a natural, but a relatively easy consequence of the model we call the inflationary universe. The inflationary universe is, in principle, testable within our observed universe. If we will find that we are convinced that this is the correct model of the behavior of our universe, and if we will show that the production of an ensemble of universes is an unavoidable part of the inflationary model, then we should, accept the fact that this ensemble
yeah,
is
yeah,
there.
yeah. No, that makes sense. Yeah. Um, let me ask you about another aspect of beauty, which is, people typically, a lot of people think beauty is in the eye of the beholder. It's very subjective, right? That's how we typically understand it. But reading some of your work, we may also perhaps see an objective dimension to beauty, right? And you've talked about the golden ratio, and perhaps there are mathematical properties of the structures that we tend to find beautiful. Um, so I wonder what do you think explains that? Could you tell us a little bit about the golden ratio for those who don't know what it is, and how it seems to work across a variety of domains, and then why it is that we seem to be hardwired to find that beautiful?
Yeah, I will disagree with the
Okay.
last statement. I will explain what the golden ratio is, but I don't think we're hardwired to find that beautiful. Um, okay, the golden ratio is very simple. I mean, and it's due to Euclid and even before him, the Pythagoreans. If you take a line and you divide it into two unequal parts in such a way that the longer part to the short, in terms of length, is the same as the whole line to the long part, then you divided it in a golden ratio. Now you can do some very, very simple algebra to show that in such a case, you divided it in such a way that the ratio between the long to the short part is a number, 1.618, and it goes on forever without repeating. So that's the golden ratio. It's this number, 1.618, and goes on forever. Um, Now, why has this number become so interesting? Well, first of all, because the ancient Greeks uh, discovered that it appears in the pentagram and in the pentagon and so on, and they thought that the pentagram was a very important symbol. It was the symbol of the Pythagoreans. So Plato talked about this, so it became something that they were talking about. Then, came, the kind of Middle Ages and so on, and a mathematician in Italy found a sequence of numbers, which is now called the Fibonacci sequence. His name was Leonardo of Pisa, and people discovered, actually Kepler, the same astronomer Kepler, first discovered that the ratio of two adjacent numbers in that sequence converges to the golden ratio. So suddenly the number appeared in things unrelated to lines and how you divide them. And then a certain guy named Luca Pacioli, uh, a priest, wrote a whole book where he called it the divine proportion. And so that generated even more interest in it, and so on. Uh, Bottom line is that throughout history, people got interested in it in a variety of ways. It started to be incorporated in certain works of art. Salvador Dali, where you are in DC, there is a painting at the National Gallery, The Sacrament of the Last Supper. The dimensions of the painting are in golden ratio, namely the length to the width of the rectangle is a golden ratio. And also above the supper table there floats a big dodecahedron, which is one of the five Platonic solids, which also has the golden ratio written all over it, and so on. So that was one example, and there are a few other such things. Um, what you referred to in terms of hardwired thing, there was a psychologist named Gustav Fechner, one of the pioneers in psychology, and he did a whole series of experiments where he asked people to rank which rectangle they find most attractive. And he found that there was a peak, albeit rather wide, around the value of the golden ratio. Now, the reason I say that not hardwired, is the following. With our eyes, we actually cannot tell the difference between, let's say, a ratio of 1.6 and the golden ratio, which is an irrational number, 1.618, and so on, gone for. We cannot tell. So it's not as if, we with our eyes, boom, zeroed in on the golden ratio. All that tells us is that we don't like rectangles that are either too narrow and long or too square. We like rectangles that have a width, a length to width ratio somewhere between 1.5 and 1.9. And yes, the golden ratio is in that range. but it's not as if, it's that number and so on. The number does appear in a variety of natural phenomena. Uh, Again, because its appearance in situation which have a fivefold symmetry, like a pentagram, pentagon, and so on. So, for example, it appears in these things called crystals, which were discovered in the 1980s, um, and which surprised everybody because uh, crystallographers did not think that you can find crystals that have a fivefold symmetry. And then when they were found by materials engineer Dan Shechtman, he eventually got the Nobel Prize for this. So they appear in a number of such phenomena. They appear in leaf arrangements of certain plants. Um, Not all plants, absolutely not. But in some plants, it appears there and so on. So yes, people got very attached to it. Many artists heard about this. There was also a Romanian author in France who, at the beginning of the 20th century, wrote a whole book about this and so on. And he was in the circles of artists, and so it became very, very famous. This number.
Yeah, yeah,
Yeah.
yeah. So it's yeah. Um, because I think people do point to it in making arguments for beauty as being something objective, that it's a property that you can find in architecture and in music, and and I wonder also whether it's culturally conditioned, whether this is a property of Western art forms.
For sure. For sure, yes, for sure. And for example, by the way, the golden ratio, while it features prominently in the West, it didn't particularly appear in Indian mathematics nor in Chinese mathematics. Didn't play a very important role. Well, even though this Fibonacci sequence appeared in some Indian poetry even before Fibonacci. So yeah. Um, so yes, it is. There are cultural things associated with it, and whether or not beauty is there is something. There are some objective criteria there, and so on. You will notice that, for example, many churches and things like this tend to be symmetric. Okay, but if you look at the paintings which are completely symmetric in terms of left-right symmetry are considered boring. Um, so we don't even have the same feeling about
Yeah,
different
right, right.
things.
That's true. We're talking about art. I see a number of art books behind you there. Tell us about the relationship between art and science in your own experience. I mean, have you found a relationship between the kind of beauty that you discover in science and in scientific theories and the kind of beauty that we see in art? Are they different kinds of things?
Yeah, I actually think there are different kind of things, but I mean that's a very personal thing. I mean, I always liked art, maybe because I don't have any talents in art, so I always had a great appreciation for art. Um, and being a scientist, I could never afford to actually buy great art. So I collect the next best thing, which is books on art, of which
Right.
I have thousands. Uh, yes, I love art. I should say that my interests have been, well, partly because of my background, more in Western art than, let's say, than in Indian or African or Asian art in general. I know a little bit about those too, and I have some books about that. But my general interest has been more on Western art, but really all forms of the visual arts. By that I mean painting, architecture, sculpture, and so on, and also from, I would say, pre-Renaissance to the present. Again, I don't look that much at ancient Egyptian art or Assyrian art, even though, again, I have an appreciation for those great works that they have done. Um, how is that? Does that relate to my science? Not a lot, to be honest. Uh, and while I have some colleagues that are equally passionate about art as I am, there are not very many. Um, so most of my colleagues, yeah, they like art at some level, but uh, they don't feel a passion about this. Um, uh, per- Perhaps I should have been born
Right,
during
right.
the Renaissance. Yeah, I would have perhaps fitted
Yeah, flourished as
better
both.
in, in that community. You see, Galileo, about whom I wrote, he did not distinguish. I mean, to him it was clear that he should be interested in art as well as in science, uh, and by that I mean not just visual arts. I mean, he was interested in poetry, for example. He wrote an entire essay comparing the poet Ariosto to the poet Tasso. He had a strong opinion. He thought Ariosto was far superior to Tasso, and he wrote an entire essay on this. He wrote an essay at the request of his painter friend. He wrote an essay comparing painting to sculpture, and he also used his art. You see, as a young boy, he actually studied drawing at the drawing school, um, and as a result, we have these fantastic wash drawings of him of the moon, which where he used his artistic understanding to understand what he was seeing, and especially light and shadow. He understood that what he was seeing, these features he was seeing, actually meant that the surface of the moon was rugged and that there were craters and mountains. He even tried to determine the height of some of the mountains of the moon, and that came really more from his artistic knowledge rather than from his
Yeah, yeah.
scientific
Wait, do you think
knowledge.
that sort of Renaissance sensibility is something that scientists today need? A kind of integration of art and science? Is that valuable or important?
I think that some of them need that, and the reason I say that, not everybody, but some need. The reason I say that is there are studies, psychological studies. In particular, there was this Chicago psychology professor. I believe he's still alive, but retired. Mihai Csikszentmihalyi, and he wrote um, a book about creativity, where he interviewed about 100 extremely creative individuals from various disciplines, for many disciplines. And uh, there were, he tried to find whether there is anything common to people who are extraordinarily creative. And there are two things that he mentions that he found. One was uh, their enormous curiosity, that they were all extremely curious people. And second, uh, a characteristic which he termed complexity, by which he meant that while most people are they're either you can be an introvert or an extrovert. Those people could be both. Sometimes they could be this, sometimes they could be that. Even in terms of masculine, feminine, he found that these people sometimes, expressed what would be regarded as very masculine characteristic, and sometimes rather feminine, what would be regarded as feminine characteristics. So this he called complexity, this ability to cross the spectrum of characteristics that he found. And so you see, what this argues for is that if you want to be very creative, what does it mean to be very curious? It means that you are interested in many things. Uh, and what we can even almost understand this, because very often creativity means the ability to borrow concepts from one area and use them in a completely different area. And so if that is true, then yes, it helps to be very curious, because then it helps you to be creative. So when I say a Renaissance person, it doesn't necessarily mean that you need to be interested in art and science, but interested in science, in your science and some other science, or in your science and music, or
Something beyond a
something
narrow
else. Yeah,
specialization where you can actually make connections. And yeah, yeah.
right.
Um, well, let's maybe for the last question, I just ask you, what do you think is the value of beauty in science? I suppose why the public should maybe care about what scientists find beautiful, and is this important?
Oddly enough, and I don't know, one shouldn't call this a law because it certainly doesn't always apply. But oddly enough, the theories that in physics, at least, which is an area that I know, which have proven to be at the end correct and successful, also enjoy uh, at least those criteria that I listed for them being beautiful. Uh, you see, I mentioned the fact that we're trying to find a theory to unify the physics of the subatomic world with the physics of the universe at large, general relativity and quantum mechanics. Well, unification means that you use symmetry and simplicity, which are the things, as I mentioned, as criteria for a beautiful theory. So, um, if we find such a theory, and so far we have found some such theories, yes, I mean, we do have the standard model of particle physics, which has already unified basically electromagnetism with the weak nuclear force and the strong nuclear force. So we already unified three of the four basic interactions that we see in nature. We have still not managed to add gravity to that, but we're using it. So we are using these um, elements of beauty, if you like, even if you don't call them beauty, but you are using these elements in the theories that we construct. So this is precisely why people such as Einstein and Wigner and others, emphasize that beauty in the science is very important. Um, that was, their feeling that at the end of the day, when you find the correct theory, it will turn out to be also quite beautiful.
Mario, thank you so much for taking the time for your insights. It's been really delightful speaking with you. This has been really such a pleasure.
My pleasure.
Hey everyone, thanks for watching. If you liked that video, please hit that thumbs up button and share it with your friends. Also, please take a second to hit the subscribe button because it really helps us out. Thanks.